Tonight, we're going to try to understand something that no human brain is actually built to understand. Step outside on a clear night and look up. You'll see a few thousand stars with the naked eye, maybe more if you're away from city lights. Each one looks like a pinprick, a tiny fixed light embedded in a black dome overhead. It feels contained, manageable even. Your brain can hold all of it at once. That feeling is wrong. Before the night is through, you'll grasp exactly why. What we're talking about is the observable universe. Not just the night sky, not just the Milky Way, the full measurable extent of everything we can detect from Earth, stretching in every direction across 93 billion light-years of space. That number sounds big. It is big. But the problem isn't really the number. The problem is that human beings aren't equipped to feel what that number actually means. We can say it. We can write it down. We cannot truly grasp it. Here's the thing most people don't realize. When scientists say the observable universe, they don't mean the whole universe. They mean the part we can see. The part where light has had enough time to reach us since the beginning of everything. Beyond that edge, the universe keeps going. We just can't observe it. We have no idea how far it extends. And that boundary, that hard wall on what we're allowed to know, is one of the most unsettling ideas in all of science. But even before we get to the edges, we have to deal with the sheer depth of what's inside. 2 trillion galaxies, not 2 trillion stars. 2 trillion galaxies, each one containing hundreds of billions of stars of their own. The math doesn't land the way it should when you read it like that. It doesn't land because it can't. Your brain evolved to track animals on a savanna, to judge distances in terms of walking, to count things in the dozens or maybe the hundreds. It did not evolve for this. Every number we're going to cover tonight is going to fight your intuition. You'll hear something astonishing. Your brain will acknowledge it, and then it will quietly file it away alongside ordinary facts because that's the only thing it knows how to do. That is the scale problem. Not that the numbers are hard to find, it's that they're almost impossible to actually feel. Tonight, we're going to try anyway. We're going to build the scale layer by layer, starting with things you already know and pushing outward until the whole structure becomes something you can't look away from. We're going to use the tools astronomers use: light, time, distance, and we're going to follow them until they lead somewhere genuinely uncomfortable. Because the universe isn't just large the way that a continent is large, or the ocean is large, or even the solar system is large. It's large in a way that breaks the categories we use to think about size. The further you go, the more the numbers stop behaving like numbers and start behaving like something else entirely. If you love thinking about the deep structure of the cosmos, please hit the thumbs up or subscribe to the channel. It helps us reach more people who want to think about exactly these kinds of questions. Now, let's begin. Let's start with what the observable universe actually is, because most people who use that phrase don't mean quite the right thing. When most people say the universe, they mean everything that exists. All of space, all of time, all matter and energy. The observable universe is something more specific than that. It's the portion of the universe we can actually see from Earth. Not because the rest is hidden behind something, not because our telescopes aren't powerful enough, but because light from the more distant regions simply hasn't had enough time to reach us yet. Here's how to think about it. The universe is about 13.8 billion years old. Light travels fast, faster than anything else in existence. But it still takes time to cross a distance. If a star is a billion light years away, The light from that star takes 1 billion years to reach your eye. That means you're seeing that star as it was 1 billion years ago. Not as it is now, as it was. The further out you look, the further back in time you're seeing. Push that idea to its limit. There's a distance at which the light hasn't had time to reach us yet at all. Light that left its source at the moment of the Big Bang, 13.8 billion years ago, has been traveling ever since. The sphere defined by how far that ancient light has traveled is what we call the cosmic horizon. It's the edge of the observable universe. Beyond it, light is still on its way. We simply haven't received it. So the observable universe is bounded by time, not just space. It's a bubble of knowable reality centered on Earth, defined by how old the universe is and how fast light travels. Now here's where people get confused. If the universe is 13.8 billion years old and light has been traveling since the beginning, shouldn't the observable universe be 13.8 billion light years in radius? That would put the diameter at roughly 27.6 billion light years. But the actual figure is about 93 billion light years across. That's a radius of about 46 billion light years. How does that work? The answer is cosmic expansion. Space itself is expanding. It's been expanding since the Big Bang, and it continues to expand today. The galaxy or region that emitted light 13.8 billion years ago wasn't 46 billion light years away when it sent that light. It was much closer. But in the time it took that light to travel to us, space expanded. That original source got carried outward by the expansion of space itself. By the time the light arrived here, the source had moved to a distance of about 46 billion light years. Think of it like walking along a moving walkway at an airport. You're moving forward under your own power, but the walkway is also carrying you. Your final position is further than your own speed alone would explain. That's roughly what happened to the light from the early universe. It traveled at light speed the whole time, but the space it was crossing kept stretching as it went. This isn't a contradiction, it's a consequence of how expansion works. The expansion of space isn't limited by the speed of light in the same way that objects moving through space are. Space itself can carry things apart faster than light can cross the gap. This is why the observable universe is 93 billion light years across rather than 27.6 billion. Now, here's the part that's important to hold on to. The observable universe is not the universe. It's just the portion of the universe we can access with light. The actual universe almost certainly extends far beyond our cosmic horizon. How far? We genuinely don't know. Some models suggest it's hundreds of times larger than the observable portion. Others suggest it could be infinite. There is no current way to measure it because by definition the light from those regions hasn't reached us. They are outside our horizon, permanently. Picture yourself standing in a foggy field at night. You can see maybe 100 meters in any direction before the fog swallows everything. The field doesn't end at the edge of your visibility. The fog just prevents you from seeing further. The field continues. How far, you can't say. Maybe it goes on for miles. Maybe it's enormous. You have no way to determine that from where you're standing. The cosmic horizon works the same way. We can see out to about 46 billion light years in every direction. That's our fog line. Beyond it, the universe continues. We can't see it. We can't measure it. We can make educated theoretical guesses, but we cannot observe it directly. The observable universe is not a wall. It's a limit on our vision. What makes this genuinely strange is that the universe beyond our horizon isn't hidden in some exotic dimension or locked behind a physical barrier. It's just space. Regular space, with presumably the same laws of physics, the same kinds of galaxies and stars and empty expanses. We can't see it simply because not enough time has passed. Give it another billion years, and light that was previously out of reach will have crossed the threshold. Our observable universe will grow. Very slowly, but it will grow. That also means the observable universe looked different in the past. A billion years after the Big Bang, the observable bubble was much smaller. Entire regions we can see today were beyond the horizon back then. The observable universe isn't a fixed thing. It's a sphere that has been expanding as the universe ages. As time goes on, more of the actual universe becomes visible to us. That said, there's a complication going in the other direction. The expansion of space isn't just happening, it's accelerating. Driven by something called dark energy, which makes up roughly 68% of the total energy content of the universe, distant regions of space are being carried away from us faster and faster. Some of those regions are already moving away from us faster than light can cross the growing gap. We will never see them, even given infinite time. In that sense, our observable universe is actually shrinking in a practical way, even as it technically continues to expand. The observable universe, then, is a snapshot, a 93 billion light-year wide sphere of reality that happens to be visible from Earth at this particular moment in cosmic history. It's bounded on one side by time, nothing before the Big Bang, and bounded on the other by a horizon defined by the age of the universe and the speed of light, complicated further by an expansion that's quietly sealing off more and more of existence from our view. But even just working with what we can see, the numbers are staggering enough. Before we can talk about how big the observable universe is, we need a unit of measurement that actually makes sense at these distances. Miles don't work. Kilometers don't work. Even billions of kilometers barely get you to the edge of our solar system. The numbers become so large they stop meaning anything. So physicists and astronomers use light instead. Specifically, they use the distance that light travels in a given amount of time. A light second, a light minute, a light year. These aren't units of time, they're units of distance. And they work because light speed is the one constant in the universe that everything else gets measured against. Here's what we're working with. Light travels at about 186,000 miles per second, or roughly 300,000 kilometers per second. That's fast enough to circle the entire Earth 7.5 times in a single second. It's the fastest thing in the universe. Nothing with mass can reach it. Nothing we've ever built has come remotely close to it. And yet, even at that speed, the distances involved in space are almost insultingly large. Let's start close. The Moon is about 239,000 miles from Earth. At the speed of light, you'd cover that in about 1.3 seconds. 1.3 seconds. If you shone a flashlight at the Moon, the beam would hit the surface in just over a heartbeat. That's our nearest cosmic neighbor, and light crosses that gap before you could finish saying the word distance. Now move out to the Sun. The Sun is about 93 million miles away, and light takes roughly 8 minutes to make that trip. 8 minutes. That means the sunlight hitting your face right now left the Sun 8 minutes ago. You're not seeing the Sun as it is. You're seeing it as it was 8 minutes in the past. This will matter much more when we start talking about objects that are thousands, millions, or billions of light years away. But even here, the delay is real. Keep going. Mars, at its closest approach to Earth, is about 3 light minutes away. At its farthest, it's closer to 22 light minutes. Jupiter sits somewhere around 35 to 52 light minutes out, depending on where both planets are in their orbits. Saturn is roughly 70 to 90 light minutes, and then things start stretching out considerably. By the time you reach Pluto, you're looking at a one-way light travel time of somewhere between 4 and 7 light hours, depending on where Pluto is in its orbit. It's worth stopping on that for a moment. Pluto is still inside our solar system. It's still gravitationally bound to our sun. And light, the fastest thing that exists, takes several hours just to get there. When the New Horizons spacecraft sent back its images of Pluto in 2015, those signals, traveling at the speed of light, took over 4 hours to reach Earth. 4 hours for a signal. Not a spacecraft, not a person. A radio signal. The edge of the solar system, defined roughly by the heliopause where the sun's solar wind stops dominating, sits somewhere around 120 astronomical units out. That's about 120 times the Earth-Sun distance. Light takes around 16 to 17 hours to reach it. So the full diameter of our solar system, edge to edge, spans roughly a day and a half of light travel time. That's our home. That's the neighborhood our sun controls. And by the time we get to the galaxy scale numbers, this entire region will be a dot. Now take one more step. The nearest star to Earth, Proxima Centauri, is about 4.24 light-years away. Not light hours, not light minutes, light years. That means light, moving at 186,000 miles per second, takes more than 4 full years to cross the gap between our sun and the next star over. The star that is, by cosmic standards, basically next door. Here's what that means in practical terms. When you look at Proxima Centauri in the night sky, you're seeing it as it was more than 4 years ago. The light hitting your eye departed that star before it even reached you. If Proxima Centauri vanished entirely tomorrow, we wouldn't know for over 4 years. If something remarkable happened there today, a planet igniting, a signal, anything, we'd wait 4 years to find out. And this is just the nearest star. There are stars in our galaxy that are tens of thousands of light years away. There are galaxies that are millions of light years away. There are structures at the edge of the observable universe that are billions of light years away. The light year is the only unit that doesn't immediately collapse under the weight of these distances, and even it starts to feel strained once you scale up far enough. This is why astronomers use it. Not because it's intuitive, it isn't, but because miles and kilometers just dissolve into meaningless strings of zeros. A light year gives you something to hold on to. It ties distance to something real, the time it takes for light to travel. And because the speed of light is a hard, universal constant, it's an anchor. It doesn't change. It gives us a stable ruler in a universe that's expanding in every direction. The moon is 1.3 light seconds. The sun is 8 light minutes. Pluto is several light hours. The nearest star is 4.24 light years. Hold those numbers in mind. They're about to seem very small. Now that we have our ruler, let's start measuring. Most people have a vague sense that the solar system is large, but vague doesn't come close to covering it. The solar system is large in a way that should genuinely unsettle you, and we're going to walk through it carefully because this is only the first layer. Start with the Earth and the Sun. The distance between them is about 93 million miles. That number is so large it's almost meaningless on its own. So let's put it into terms that make more sense. If you could drive a car at highway speed, 60 miles per hour without stopping, it would take you about 177 years to reach the sun. Not days, not months, years. Nearly 2 centuries of driving non-stop just to reach the nearest star. And the sun is our closest star. It's practically in our front yard by cosmic standards. Light covers that same distance in just over 8 minutes. Even at the speed of light, it takes time. Now let's move outward. Mars, at its closest approach to Earth, sits about 140 million miles away. At its farthest, it's closer to 250 million miles. That's the planet we talk about sending humans to within the next few decades. The journey would take somewhere between 6 and 9 months with current propulsion technology. For just the next planet over, not a distant world. The next one. Jupiter is a different story entirely. The largest planet in the solar system sits roughly 484 million miles from the Sun on average. When the Voyager probes flew past Jupiter in 1979, they'd already been traveling for nearly 2 years. Saturn is even farther out, averaging about 886 million miles from the Sun. The rings of Saturn, which look delicate and close in photographs, span roughly 282,000 miles across. That's larger than the distance from Earth to the Moon. The Moon, which took Apollo astronauts 3 days to reach, could fit inside Saturn's ring system. Uranus and Neptune push the boundaries further. Neptune, the outermost recognized planet, orbits at an average of about 2.8 billion miles from the Sun. Light takes roughly 4 hours to reach Neptune from the Sun. When we communicate with spacecraft near Neptune, we're waiting hours for signals to arrive and hours more for any response. That's a conversation with a delay measured not in milliseconds, but in entire afternoons. But the planets aren't even the edge of it. Beyond Neptune lies the Kuiper Belt, a region of icy objects and dwarf planets stretching from about 30 to 50 astronomical units from the Sun. 1 astronomical unit is the average Earth-Sun distance, that 93 million miles we started with. So the Kuiper Belt extends to roughly 50 times the Earth-Sun distance. Pluto lives in this zone, orbiting at an average of about 39 astronomical units. New Horizons, the spacecraft we launched specifically to visit Pluto, took 9.5 years to get there. 9.5 years at roughly 36,000 miles per hour, and it still only barely reached the inner edge of what you might call the outer solar system. The actual edge of the solar system, where the Sun's influence finally gives way to interstellar space, is called the heliopause. It sits at roughly 120 astronomical units from the Sun. That's 120 times the Earth-Sun distance, or about 11 billion miles. The heliopause is where the solar wind, the constant stream of charged particles flowing out from the Sun, finally becomes too weak to push back against the interstellar medium. Cross that boundary and you're no longer in the Sun's domain. This represents the true frontier of our cosmic neighborhood, the point where the Sun's power to shape and control the space around it finally exhausts itself. Nothing humanity has built has ventured much beyond this threshold, except for one remarkable spacecraft, one that took nearly 4 decades to accomplish what remains one of our greatest achievements. Voyager 1 crossed that boundary. Voyager 1 was launched in 1977. It flew past Jupiter in 1979, Saturn in 1980, and then just kept going. It's been traveling for nearly 50 years. It's the farthest human-made object from Earth. And in 2012, it finally crossed the heliopause and entered interstellar space. Think about that. Nearly half a century of continuous travel at speeds far beyond anything a commercial aircraft could dream of, and Voyager 1 has only just left our solar system. Here's where things get genuinely humbling. Voyager 1 is currently moving at roughly 38,000 miles per hour. That's fast. Faster than almost anything humans have ever built, though the Parker Solar Probe has now edged past it at peak velocity. But 38,000 miles per hour in the context of interstellar space is essentially nothing. If Voyager 1 were pointed directly at Proxima Centauri, and it's not, it's heading in a completely different direction, it would take approximately 70,000 years to get there. 70,000 years. Agriculture was invented about 12,000 years ago. The last ice age ended around 11,700 years ago. Our entire civilizational story, everything from the first cities to the internet, fits inside a window about 5,000 years wide. Voyager 1 would need 14 times that entire span just to reach the nearest star system, and it's already been flying for 50 years. The solar system that feels so vast when we talk about billion-mile distances and decade-long travel times. That system occupies a sphere roughly 120 astronomical units across at its functional edge. The nearest star is 4.2 light-years away. 1 light-year is about 63,000 astronomical units. So the nearest star is sitting at a distance of roughly 265,000 astronomical units from us. Our entire solar system, from the Sun to the heliopause, fits inside that gap more than 2,000 times over. When you plot our solar system on a map of even just the local stellar neighborhood, the few dozen star systems within 15 or 20 light-years of Earth, it vanishes. It becomes a single point. All of that scale we just walked through, all those billions of miles and decades of travel time, compresses down to a dot so small it barely registers on the diagram. And the solar system is just our backyard. Our solar system is one of somewhere between 100 and 400 billion star systems inside the Milky Way. That number is worth pausing on. Not 100 billion stars. Not 400 billion. Somewhere between the two, and we genuinely don't know exactly where in that range the truth falls. What we do know is that every single one of those stars is a sun. Some are smaller and dimmer than ours. Some are vastly larger, burning hotter, living shorter lives. Many of them almost certainly have planets. And all of them are inside the same galaxy we call home. The Milky Way is roughly 100,000 light-years across. We already established that a light-year represents the distance that light covers during an entire year, about 5.88 trillion miles. So when we say the galaxy is 100,000 light-years wide, we're saying that even light, the fastest thing in the universe, would take 100,000 years to cross it from one edge to the other. Not 100,000 hours, not 100,000 days, 100,000 years. For context, modern humans have only existed for about 300,000 years. Crossing our galaxy at the speed of light would take a third of all of human history just to travel from one side to the other. Our sun sits roughly 26,000 light-years from the galactic center. That puts us in the outer regions of the galaxy, about halfway between the core and the edge, in a region called the Orion Arm. We're not at the center, we're not at the fringe. We're somewhere in the middle, in one of the galaxy's spiral arms, orbiting the galactic center at a speed of about 515,000 miles per hour. At that speed, one full orbit of the galaxy takes our solar system approximately 225 million years. That's called a galactic year, and since Earth formed, we've completed fewer than 20 of them. The structure of the Milky Way is something most people have never really visualized clearly. Because we're inside it, we can't photograph it from the outside. What we know about its shape comes from mapping the positions of stars and gas clouds around us and inferring the larger structure. What we've pieced together is a barred spiral galaxy. At the center is a dense, elongated bar of stars. From the ends of that bar, several spiral arms curve outward like the arms of a pinwheel. Our own Orion arm branches off one of the major arms. Surrounding the entire disk is a spherical halo of older stars and globular clusters, ancient, tightly packed groups of hundreds of thousands of stars, orbiting the galaxy like satellites. At the very center of the Milky Way sits something that doesn't behave like anything else we know, a supermassive black hole called Sagittarius A star, containing roughly 4 million times the mass of our Sun, compressed into a region smaller than our solar system. The stars near the galactic core orbit it at extraordinary speeds, completing full orbits in just a few years. We can't see it directly from Earth because thousands of light years of gas and dust sit between us and the core. But we know it's there. The gravity of this object is so intense that nothing can escape once it crosses the event horizon, not even photons of light. Yet paradoxically, studying the orbits of stars around it has given us some of our strongest evidence that black holes actually exist. The motion of these stars follows the precise mathematical predictions that general relativity makes about how matter should behave near such an object. This alignment between observation and prediction represents one of the great confirmations of Einstein's theory of gravity. Now here's where the scale becomes genuinely hard to process. The distance from Earth to the nearest star, Proxima Centauri, is 4.24 light years. We've already talked about how that alone would take our fastest spacecraft 6,700 years. The Milky Way is 100,000 light years across. That means the galaxy is roughly 23,000 times wider than the distance to our nearest neighbor. If the gap between us and Proxima Centauri already feels impossible to cross, the full width of the galaxy is 23,000 times more impossible still. Think about it this way. Imagine you shrink the entire solar system out to the edge where Voyager is drifting, down to the size of a quarter, a single coin sitting in your palm. At that scale, the Milky Way would be roughly 120 miles across. The solar system, everything we've ever visited with a spacecraft, everything we've ever seen up close, shrinks to the size of a coin inside a galaxy that stretches from one side of a large state to the other. The total number of stars in that space is hard to hold in your mind. Estimates put it between 100 and 400 billion. If you tried to count them at 1 per second, counting non-stop without sleeping, it would take you over 3,000 years to reach 100 billion. That's counting every second of every day through all of recorded history, and you still might not be done. Most of those stars we'll never know anything about. We haven't named them. We haven't pointed telescopes at them. We don't know if they have planets, if those planets have atmospheres, if something somewhere on one of them is looking back in our direction. The Milky Way is full of possibilities that are, for all practical purposes, completely beyond our reach. Now step back even further. The Milky Way is not the only galaxy in its neighborhood. The nearest major galaxy to us is Andromeda, also called M31. It's a spiral galaxy, larger than the Milky Way, containing perhaps 1 trillion stars, and it's 2.5 million light-years away. That's not 2.5 million miles, not 2.5 million astronomical units, 2.5 million light-years. At the speed of Voyager, getting there would take somewhere in the range of 50 billion years. The current age of the universe is 13.8 billion years. We don't have 50 billion years. The universe as we know it won't look anything like this in 50 billion years. Even light takes 2.5 million years to cross that gap. When the light we receive from Andromeda tonight left that galaxy, our ancestors weren't fully human yet. The entire span of human civilization, everything we've built and learned and recorded, fits inside a fraction of the time that light took just to travel between 2 neighboring galaxies. Andromeda is visible to the naked eye on a dark night. It looks like a faint smudge near the constellation Perseus. That smudge is 1 trillion stars. It's been there every night for all of human history. We just didn't know what it was for most of that time. And the Milky Way, enormous as it is just one galaxy. The Milky Way isn't alone. In fact, our galaxy is part of a larger structure, a collection of galaxies gravitationally bound together called the local group. It contains roughly 54 galaxies in total. Most of them are small, dim, and unremarkable. Dwarf galaxies with only a few billion stars scattered around the edges of the group. But 2 members dominate everything else. The Milky Way is one. Andromeda is the other. You've probably heard of Andromeda. It's the most distant object visible to the naked eye, a faint smudge of light in the northern sky. What you're seeing when you look at it is the combined glow of roughly 1 trillion stars, all compressed by distance into something that barely registers on a clear night. Andromeda sits about 2.537 million light-years away. That light left before anatomically modern humans existed. It's been traveling toward your eye since before our species walked the Earth. Andromeda is actually larger than the Milky Way. It spans somewhere around 220,000 light-years across, compared to our galaxy's roughly 100,000 light-years, and it's moving toward us. Right now, Andromeda is closing the gap at about 110 kilometers per second. In approximately 4.5 billion years, these 2 galaxies will collide and eventually merge into a single, larger, elliptical galaxy. Some astronomers have already given this future galaxy a name, Milkomeda. The collision won't destroy stars. The distances between individual stars are too vast for direct impacts to be common. But it will reshape both galaxies entirely, disrupting their spiral structures and scattering billions of stars into new orbits. Our solar system will almost certainly survive, but it may end up in a completely different region of the merged galaxy than it occupies today. It's a slow-motion catastrophe on scales of time we can't really feel. Now, the other members of the local group are worth knowing. Closest to us are the Magellanic Clouds, the large and the small. These are satellite galaxies of the Milky Way, gravitationally locked in orbit around us. If you're in the southern hemisphere on a clear night, you can see both of them without a telescope. They look like detached pieces of the Milky Way. The large Magellanic Cloud sits about 160,000 light-years away. The small Magellanic Cloud is around 200,000 light-years out. Both are irregular dwarf galaxies, meaning they don't have the organized spiral structure of the Milky Way or Andromeda. They're messy star-forming regions, and astronomers study them closely because their relative proximity makes them easier to observe in detail than more distant galaxies. In 2006, researchers discovered that the Magellanic Clouds may actually be just passing through the neighborhood, rather than being permanent satellites. The data suggested they might be moving too fast to remain gravitationally bound to us over the long term. It's still debated, but it raised the possibility that what we assumed were permanent companions might eventually drift away. Beyond the Magellanic Clouds, there are dozens of other dwarf galaxies associated with the local group. The Triangulum Galaxy, also called M33, is the third largest member after the Milky Way and Andromeda, sitting about 2.7 million light-years away. It's a spiral galaxy, but a modest one, maybe 40 billion stars compared to Andromeda's trillion. There are also galaxies like the Sculptor Dwarf, the Fornax Dwarf, and Canis Major Dwarf, which is so close to us. Only about 25,000 light-years from Earth's galactic center, that it may technically be inside the outer disk of the Milky Way itself. The full extent of the local group spans roughly 10 million light-years. 10 million light years from one edge to the other. That number should sound large. It is large. By any human standard, 10 million light years is incomprehensible. But here's the thing most people don't realize. Against the broader scale of the observable universe, the local group barely registers. All 54 galaxies, the Milky Way, Andromeda, the Magellanic Clouds, every dwarf galaxy drifting in between. The entire structure fits inside a region that represents a tiny fraction of a percent of what we can observe. Think about that for a second. Our galaxy is 100,000 light years across. It takes your breath away just to sit with that number. But then you zoom out and see that our galaxy, along with 53 others, forms a group that spans 10 million light years. And that group is still essentially local, still our immediate neighborhood, still a structure that barely shows up when you pull back to the full map. This is the thing that makes cosmic scale genuinely hard to hold in your mind. Each layer is so much larger than the last that the previous layer vanishes. The distance from Earth to the Moon felt enormous until you learned the distance to the Sun. The solar system felt vast until you learned how far away the nearest star is. The Milky Way felt incomprehensible until you compared it to Andromeda. And now we're looking at the entire local group. 10 million light years of gravitationally connected galaxies. And we're about to zoom out again. The local group is our home in the largest sense. Everything we've ever observed closely, everything our telescopes have reached with any real detail, everything we might ever hope to reach with any technology we can currently imagine. It's all in here. All of it. And still. But even the entire local group is just a speck against what comes next. Galaxies don't float in space in isolation. They cluster together, pulled by gravity, into enormous collections that make the local group look like a small gathering. These structures are called galaxy clusters. They represent the next major level of organization in the universe, bigger than anything we've talked about so far by a significant margin. The nearest large example is the Virgo cluster. It sits about 65 million light years away from us. That is already a number that should stop you cold. Remember that the entire local group spans roughly 10 million light years. The Virgo cluster is 6 times farther away than the full width of our own galactic neighborhood, and it contains more than 1,300 galaxies, all gravitationally bound together, orbiting a common center of mass. The largest of them is a giant elliptical galaxy called M87, that you may have heard of for another reason entirely. It's the galaxy that harbors the first black hole humanity ever directly photographed. But we'll get to black holes later. For now, just sit with that number. Over 1,300 galaxies, each one containing hundreds of billions of stars, all packed into a single cluster. Here's what makes this even harder to process. The Virgo cluster isn't some distant, unrelated structure. It's our cluster. The Milky Way and the rest of the local group are gravitationally associated with the Virgo cluster, part of a much larger structure called the Virgo supercluster. A supercluster is exactly what it sounds like, a cluster of galaxy clusters. Superclusters are among the largest structures in the known universe. The Virgo supercluster, which contains the Virgo cluster along with dozens of other galaxy groups and clusters, including our own local group, spans roughly 110 million light years across. That is a number that no human mind is really equipped to absorb. But we're not done yet. In 2014, a team of astronomers redrew the boundaries of our cosmic neighborhood, using a new technique that mapped the flow of galaxies through space, not just their positions. but the gravitational currents pulling them. They identified a structure even larger than the Virgo supercluster. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. And the name fits. Laniakea is the supercluster within which the Virgo supercluster sits as just one component. It spans approximately 520 million light-years and contains the mass equivalent to 100 million billion suns. Written out, that's 100 quadrillion solar masses. The number essentially loses meaning before you finish saying it. Laniakea contains about 100,000 galaxies in total. Our Milky Way is somewhere near its outer edge, slowly drifting toward the gravitational center, a region astronomers call the Great Attractor. We've known about the Great Attractor since the 1970s, when astronomers noticed that our entire local group is being pulled in a specific direction at around 1.4 million miles per hour. For a long time, figuring out what was doing the pulling was difficult. This was because we're looking straight through the densest part of the Milky Way's disk, which blocks our view. What we now know is that the Great Attractor corresponds to the Norma cluster, a massive galaxy cluster sitting about 150 to 250 million light-years away. And even that cluster is itself being pulled toward something bigger, the Shapley supercluster, a concentration of galaxies so massive it's one of the dominant gravitational influences across hundreds of millions of light-years. So we have a galaxy in a group in a supercluster being pulled toward a cluster. That is being pulled toward an even larger concentration of mass. Every layer you add makes the previous layer feel smaller. Now let's talk about what lies between all of these structures, because that's where things get genuinely strange. If you could zoom out far enough to see galaxy clusters and superclusters as individual objects, you'd notice something striking about how they're arranged. They're not spread evenly through space. They form long, thread-like filaments, enormous chains of galaxies and clusters stretching across hundreds of millions of light-years. Where these filaments intersect, you get the densest concentrations of galaxies. And between the filaments, almost nothing. Vast, empty regions called cosmic voids, where very few galaxies exist at all. The Bode's void is one of the more dramatic examples. It spans roughly 330 million light-years and contains almost no galaxies. To put that in perspective, if our Milky Way were located at the center of the Bode's void, we wouldn't have known there were other galaxies at all until the 1960s. This was because the nearest ones would be so far away they'd have been beyond our detection technology. The void is that empty. This large-scale structure, filaments of galaxies surrounding vast empty voids, is sometimes called the cosmic web. And it's not random. The pattern reflects the distribution of matter in the very early universe, stretched and amplified over 13.8 billion years of gravity doing its work. The filaments trace the edges of enormous bubbles. The voids are the insides of those bubbles. The whole thing resembles a three-dimensional foam when you look at it in simulation, with galaxy clusters sitting at the junctions where the bubble walls meet. What drives this structure is dark matter. The filaments you see in galaxy distribution maps aren't just made of visible matter. They're threaded through with enormous concentrations of dark matter that we can't see directly but can detect through its gravitational effects. The dark matter filaments formed first. Ordinary matter, gas, dust, eventually stars and galaxies, fell into them along the path of least resistance. The cosmic web is, in a real sense, a map of dark matter as much as it is a map of galaxies. The scale of all this is worth pausing on for a moment. Laniakea alone is 520 million light-years across. If you could somehow travel at the speed of light, which is impossible for anything with mass. But let's pretend, Crossing Laniakea from one end to the other would take 520 million years. For context, 520 million years ago on Earth, the Cambrian explosion had just occurred. Complex animal life had barely begun. You would have spent the entire history of complex life on this planet just crossing our supercluster. And Laniakea is not particularly unusual. There are other superclusters spread across the observable universe: the Shapley supercluster, the Perseus-Pisces supercluster, the Coma supercluster. All of them comparable in scale, all connected by the same filamentary structure, all separated by the same vast voids. The cosmic web is not a local feature, and this cosmic web stretches across the entire observable universe. So here's the number we've been building toward. The observable universe is 93 billion light-years in diameter, not 93 million, not 93 billion miles, 93 billion light-years. Each of those light-years is about 5.88 trillion miles. Take a moment with that. We've already established that a single light-year is a distance so vast that our fastest spacecraft would need thousands of years just to cover one of them. Now multiply that by 93 billion. The number doesn't fit in your head. It's not supposed to. Human brains evolved to track prey across a savanna, to judge distances of maybe a few miles at most. We are not equipped for this, but let's try anyway. Inside that 93 billion light-year sphere, astronomers now estimate there are approximately 2 trillion galaxies. That number was revised upward significantly in 2016 when researchers at the University of Nottingham analyzed deep-field images from the Hubble Space Telescope and concluded that previous estimates had undercounted by a factor of roughly 10. Earlier models suggested around 200 billion galaxies. The real number appears to be closer to 2 trillion. Most of those galaxies are small, faint dwarf galaxies too dim for our current telescopes to detect directly. We infer their existence from models of how structure forms in the universe. 2 trillion galaxies, and most of them are essentially invisible to us right now. Each of those galaxies contains stars. The number varies enormously. Dwarf galaxies might hold a few billion stars. A large elliptical galaxy like IC 1101, one of the biggest known, contains somewhere around 100 trillion stars. Our own Milky Way sits somewhere in the middle, with between 100 and 400 billion stars. For the purposes of calculating a total, astronomers use a conservative average of around 100 billion stars per galaxy. So take 2 trillion galaxies. Multiply by 100 billion stars each. The result is 200 sextillion stars. Some estimates push closer to 300 sextillion when accounting for larger galaxies and revised galaxy counts. That's a 2 or 3, followed by 23 zeros. Here's a way people often try to make that feel real. Count the grains of sand on every beach on Earth, every coastline, every desert, every sandbox. The estimated number of grains is around 7.5 times 10 to the 18th power. That's 7.5 quintillion grains of sand. It's an almost meaningless number on its own. But compare it to the star count. There are roughly 10,000 to 40,000 times more stars in the observable universe than grains of sand on every beach on Earth. Not a few times more. Not double or triple. 10,000 times more. The stars don't just win that comparison. They win it so thoroughly that the sand analogy stops being useful and starts being embarrassing. It was supposed to help you grasp the number, and instead it just reveals how far out of reach the number actually is. Try it from another direction. Suppose you could count stars at the rate of 1 per second, without sleeping, without stopping. At that pace, counting to 1 billion takes about 31 years. Counting to 1 trillion takes 31,000 years. Counting to 1 sextillion would take roughly 31 million years. The estimated stellar count is somewhere between 200 and 300 sextillion. You would need 6 to 9 billion years of non-stop counting. That's longer than the Earth has existed. You would start counting before our planet formed and finish after the Sun begins its death sequence, and you would not quite be done. That's the number of stars we're talking about. And each of those stars is a sun. Not a point of light, a sun. A massive ball of nuclear fire, fusing hydrogen into helium, radiating energy across billions of miles in every direction. Many of them are larger than our own. Some are hundreds of times larger. Some are so massive they burn through their fuel in just a few million years before dying in explosions that briefly outshine entire galaxies. And around a significant fraction of those stars, there are planets. The Kepler Space Telescope's findings suggest that on average, every star in the Milky Way hosts at least one planet. Apply that to 200 sextillion stars and you start to arrive at numbers that genuinely have no human-scale analogy left to offer. Let's stay with the galaxy count for a moment, because 2 trillion is hard enough on its own. If you wanted to visit every galaxy in the observable universe, spending just 1 second at each one, the trip would take 63,000 times the current age of the universe. The universe is 13.8 billion years old. You would need roughly 63,000 of those lifetimes just to check in briefly at every galaxy we know exists. Not to explore them, not to count their stars, just to visit and immediately move on. Here's another way to feel the number. The Hubble Ultra Deep Field is one of the most famous images in astronomy. Hubble pointed at a tiny, apparently empty patch of sky, a region about 1/13 millionth of the total sky, and held that exposure for over 11 days. What came back was an image containing roughly 10,000 galaxies. 10,000 galaxies in a sliver of sky that looks completely blank to the naked eye. Every direction you look, at any patch of darkness you choose, there are thousands of galaxies sitting behind it. You just can't see them without help. The night sky isn't empty, it's full. Every gap between the visible stars contains more galaxies than you could count in an afternoon. What makes this genuinely difficult to sit with isn't just the size, it's what the size implies. If the observable universe contains 2 trillion galaxies and each galaxy contains hundreds of billions of stars, then the odds that life arose only here, only on this one planet, seem almost indefensible. We'll get into that in more detail later, but even setting that question aside, the scale itself carries a kind of weight. Everything that has ever happened to a human being, every war, every discovery, every moment of love or grief or ordinary Tuesday afternoon, took place on a single planet orbiting one star among 200 sextillion. Not a special star, not a central one. A fairly ordinary one, in the outer arm of a fairly ordinary galaxy, which is itself one of 2 trillion. There is no frame of reference that makes this feel small. The Grand Canyon feels enormous when you stand at its edge. The Pacific Ocean feels endless when you're in the middle of it. These are the largest things most people ever physically encounter. The Pacific Ocean is about 64 million square miles. The observable universe is incomprehensibly larger than that comparison even begins to suggest. The ratio between the Pacific Ocean and the observable universe is so lopsided that the ocean effectively disappears. All of Earth disappears. The entire solar system disappears. Even the Milky Way, with its 100,000 light-year span, is less than a grain of sand compared to the full 93 billion light-year diameter of what we can observe. And none of this is speculation. These aren't theoretical numbers drawn from models that might be wrong. The 93 billion light-year figure comes from well-established cosmology, confirmed by multiple independent lines of evidence. The galaxy count comes from real observations refined over decades. The stellar estimates come from direct measurement and statistical modeling of the galaxies we can actually see. This is what's out there. This is the confirmed, measured, photographed reality of the universe we inhabit. We are not at the center of it. There is no center technically, but we are certainly not at any privileged location. We are somewhere in it. One species, on one planet, around one star, inside one galaxy, among 2 trillion. And the most unsettling part isn't the size of the number. It's that the number is real. It refers to actual things that exist, and our brains cannot hold it. We can write it down, we can calculate it, we can verify it, but we cannot picture it. No one can. 2 trillion galaxies, each with hundreds of billions of stars, and we can't even properly picture one of them. There's something about the observable universe that doesn't seem to add up. We've established that the universe is 13.8 billion years old. We've established that the observable universe is 93 billion light-years across. And if you're paying attention, those two numbers shouldn't be able to coexist. If nothing moves faster than light and the universe is only 13.8 billion years old, then light could only have traveled 13.8 billion light-years in any direction since the Big Bang. The observable universe should be roughly 27 or 28 billion light-years across at most. So where does 93 billion come from? Here's the thing most people don't realize. The universe isn't just full of things moving through space. Space itself is moving, expanding, stretching in every direction simultaneously. And that changes everything about how we measure cosmic distances. Think about what the Big Bang actually was. It wasn't an explosion that sent matter flying outward into empty space. There was no empty space for matter to fly into. The Big Bang was the beginning of space itself. And from that first moment, space has been expanding, not from a central point, but everywhere at once. Every region of space is getting slightly larger. Galaxies aren't moving through space away from us. Space between us and those galaxies is growing. That's a distinction that sounds subtle but has enormous consequences. In the immediate aftermath of the Big Bang, everything was compressed into an almost unimaginably small, hot, dense region. As space expanded, it carried matter with it. And in the very early universe, space was expanding extraordinarily fast. The regions that would eventually become the farthest galaxies we can see today were carried outward while light from those regions was simultaneously trying to reach us. It's like trying to reach the end of a rubber band while someone is stretching it. You can make progress, but the destination keeps moving. Edwin Hubble figured out a key piece of this in 1929. He noticed that distant galaxies were all moving away from us, and the farther away they were, the faster they were receding. This relationship became known as Hubble's law. For every additional megaparsec of distance, roughly 3.26 million light-years, a galaxy moves away from us about 70 kilometers per second faster. That number, the Hubble constant, tells us the rate at which the universe is expanding. What this means in practice is startling. A galaxy that's 1 billion light-years away is receding at a certain speed. A galaxy that's 2 billion light-years away is receding at roughly twice that speed. Keep extrapolating, and at some distance, a galaxy is receding from us at the speed of light itself. That distance is called the Hubble horizon, and it sits at roughly 14 billion light-years from Earth. Beyond that line, galaxies are moving away from us faster than light can travel toward us. Not because they're breaking any physical laws. Nothing is actually moving through space faster than light. But space between us and those galaxies is expanding so rapidly that light from those regions can never close the gap. It's running up an escalator that's moving faster than it can climb. This is why the observable universe is 93 billion light-years across, despite light only having 13.8 billion years to travel. The regions at the edge of what we can observe were much closer to us when they emitted the light we're now receiving. By the time that light reached us, the universe had expanded so dramatically that those regions are now 46 billion light-years away in every direction. The 93 billion light-year figure accounts for where those regions are now, not where they were when the light left. That light has been traveling toward us for nearly 13.8 billion years. The regions it came from have been racing away the entire time. So when astronomers talk about the cosmic microwave background, the faint radiation left over from the early universe, essentially a photograph of what existed around 380,000 years after the Big Bang, they're looking at light from regions that are now roughly 46 billion light-years away. The universe was small enough then that light could reach us. But those regions have since been carried so far by expansion that we can't meaningfully communicate with them in any direction. And here's where it gets genuinely unsettling. The Hubble horizon isn't the edge of the observable universe. It's something different. Galaxies beyond the Hubble horizon, the ones receding faster than light, can still send us signals under the right conditions if they were closer to us when they emitted that light. The actual edge of the observable universe, the cosmic horizon, is determined by which regions had light that could reach us given the entire history of cosmic expansion. That's the 46 billion light-year boundary. But the expansion isn't slowing down, it's accelerating. In 1998, astronomers discovered that distant supernovae were dimmer than expected. They were farther away than they should have been, meaning the universe's expansion was speeding up rather than slowing down under gravity. Something was pushing space apart faster and faster. That something is what physicists call dark energy, and it makes up roughly 68% of the total energy content of the universe. Because the expansion is accelerating, the cosmic horizon is actually shrinking over time in a meaningful sense. Galaxies that are currently visible to us, galaxies whose light is right now making its way toward Earth, will eventually be carried beyond our reach. In the far future, their light will no longer be able to close the expanding gap between us. They'll cross our cosmic horizon. And once they do, they're gone from our observable universe forever. Astronomers estimate that roughly 97% of the galaxies currently within our observable universe are already moving away from us faster than light. We can still see them because the light they emitted long ago when they were closer is still reaching us. But no new information from those galaxies is ever coming. Whatever is happening in those galaxies right now, whatever has happened in them for billions of years, we'll never know. That information is permanently out of reach. There are galaxies we can see tonight whose present state, whose current existence or non-existence is something we will never learn. They might have merged. Their stars might have died. They might be gone entirely. We're looking at the past, and the present is inaccessible. Some estimates suggest that in about 2 trillion years, if any civilization still exists in our galaxy, the only galaxies they'll be able to observe will be the ones gravitationally bound to us locally, the members of what remains of the local group. Every other galaxy in the universe will have been carried beyond the horizon. The night sky will appear empty. No evidence will remain that the universe contains 2 trillion galaxies. no evidence will remain that the cosmic web exists. A civilization born that far in the future would have no way of knowing what we know right now. The universe will have hidden itself from them completely. That is not a comfortable thought. What we can see is not the universe. It's a bubble defined not by walls or edges, but by the simple, cold geometry of light speed and expansion. Outside that bubble, space continues, galaxies continue. Whatever structure the universe has on scales beyond our horizon continues. We have no access to it. We have no way of getting access to it. We can't even send a signal that would arrive before the expansion makes the distance uncrossable. Somewhere out there, beyond our cosmic horizon, the universe continues, and we will never know what it contains. The observable universe is not the universe. That distinction sounds simple, but it's worth sitting with because most of us, when we hear the word universe, picture everything that exists. All of space, all of matter, all of time. And what we actually mean when we say observable universe is something far more limited than that. It's the bubble of reality we can see from here, the part of existence where light has had time to reach us. Everything beyond that horizon isn't gone, it isn't empty. We just can't see it. So what's out there? The honest answer is that we don't know. But physicists have some ideas, and even the conservative ones are staggering. The simplest possibility is that the universe beyond our horizon looks more or less like what we can see. More galaxies, more stars, more empty space, more of the same large-scale structure we've mapped closer to home. If that's the case, then the full universe is almost certainly much larger than our observable portion. How much larger? Some estimates, based on the geometry of the universe and measurements of its curvature, suggest the full universe is at least 250 times larger than the observable bubble we inhabit. That would make it at least 23 trillion light-years across, minimum, and that's a conservative lower bound. Other models push that number far higher. Here's the thing about the curvature measurements we've taken. The universe appears to be geometrically flat. Not flat like a table, flat in the mathematical sense, meaning its geometry doesn't curve back on itself the way a sphere does. If the universe were curved like a sphere, it would be finite. You could travel far enough in one direction and eventually return to where you started. But a flat universe can be infinite. Truly, endlessly infinite, stretching on without any boundary, without any edge, forever. If the universe is infinite, then everything we've discussed tonight, the 2 trillion galaxies, the 93 billion light-year diameter, the hundreds of sextillions of stars, all of that is a single finite slice of something that never ends. Every number we've given you would be not the total count, but just the local sample. And the math gets strange from there. In an infinite universe with matter distributed roughly the way it is here, there are almost certainly other regions that look exactly like our own. Same galaxies, same stars, same planets. Somewhere out there, in principle, a region of space exists that is statistically identical to the observable universe we live in. The laws of probability, taken to infinity, produce that outcome. It's a deeply uncomfortable idea, and physicists debate how seriously to take it. Some researchers have labeled this the doppelganger problem, the troubling implication that somewhere in the infinite expanse, there exist perfect copies of you, of me, of this exact conversation occurring at this exact moment. As deeply unsettling as this seems, the mathematics of infinite space with finite variations makes it nearly inevitable. But there's another framework that pushes things even further. It comes from cosmic inflation. You'll hear more about inflation in a later section, but the core idea is that in the very first moments after the Big Bang, the universe expanded at an almost incomprehensible rate. It grew by an enormous factor in a tiny fraction of a second, and some models of how that inflation worked suggest it didn't stop everywhere at once. In most places, inflation ended, and a universe like ours formed. But in other regions, inflation kept going, and kept going. Those regions expanded so fast that they became completely disconnected from our own, moving away faster than light, unreachable, invisible, cut off permanently. Each one could have formed its own pocket universe with its own conditions, its own physical laws, its own fundamental constants. This is what cosmologists call eternal inflation, and the landscape of universes it produces is called the multiverse. Now, to be clear, the multiverse is not established science. It's a theoretical framework, a prediction that falls out of certain inflation models, but one we have no direct way to test. You can't see other universes. You can't send signals to them. You can't confirm they exist. Some physicists find the idea compelling precisely because it explains certain features of our universe that would otherwise seem like extraordinary coincidences. Others find it deeply unsatisfying for exactly the same reason. If you can't test it, it doesn't belong in physics. That debate is ongoing. What makes the multiverse compelling to some physicists is that it naturally explains why our universe's physical constants seem so precisely calibrated for the emergence of complexity and conscious observers. Without invoking a multiverse, these constants appear as profoundly unlikely cosmic coincidences. But whether or not the multiverse is real, the point stands. The observable universe is just one region of a larger whole, and we have no reliable way to know how large that whole actually is. Think about what that means. We've spent this entire video stacking impossibly large numbers on top of each other. Billions of light years, trillions of galaxies, sextillions of stars. Each number seems like the final answer until the next one makes it look small. And now we're telling you that all of that, every galaxy we can map, every photon we can detect, every piece of the universe we can ever observe, might be a vanishingly small fraction of something we can never fully measure. Our 93 billion light-year bubble might be to the full universe what a single grain of sand is to every beach on Earth, or smaller. There's no way to know. What's strange is that this isn't a failure of science. It's a hard physical limit. The cosmic horizon isn't something better telescopes will solve. It exists because information can only travel at the speed of light, and the universe has only been expanding for 13.8 billion years. There is a wall, and the wall is permanent. Beyond it, there might be more of the same. There might be regions where the laws of physics are slightly or radically different. There might be pocket universes born from inflation that have no relationship to ours. There might be something no human framework has ever imagined, because we built our frameworks from what we can see. Or the universe beyond the horizon might be just more of this. More silence, more distance, more stars slowly burning through their fuel in the dark. We just don't know. Now let's think about time instead of distance, because the time scales of the universe are just as hard to process as the distances. We've spent a lot of time talking about how big the observable universe is in space, but the universe has another dimension that's equally staggering: time. And when you start looking at the actual timeline of the universe, past and future, the same kind of vertigo sets in. The universe is 13.8 billion years old. That's the number cosmologists have arrived at through multiple independent lines of evidence. The cosmic microwave background, the ages of the oldest stars, the expansion rate of the universe, they all point to the same answer: 13.8 billion years. That number is hard enough to sit with on its own. But here's what makes it genuinely disorienting. Modern humans have existed for about 300,000 years. That sounds like a long time. It isn't. If the entire age of the universe were compressed into a single calendar year, humans would appear in the last 8 minutes of December 31st. All of recorded civilization, every empire, every war, every invention, every book ever written, fits inside the last 13 seconds of that year. 5,000 years of human history, 13 seconds. The pyramids were built 13 seconds before midnight on the last day of a year that started 13.8 billion years ago. That's where we are. And yet, here's the thing most people don't realize. The universe is not old, not in terms of what's still ahead. We are, cosmologically speaking, in the early universe. The universe as it exists today, full of stars, galaxies, light, heat, is a young and temporary phase. What comes after makes 13.8 billion years look like an opening act. The sun has roughly 5 billion years of hydrogen fuel remaining. In about 5 billion years, it will exhaust that fuel, expand into a red giant large enough to swallow Mercury and Venus and possibly Earth, and then collapse into a white dwarf, a cooling, fading ember. The solar system as we know it will be unrecognizable, but the universe will barely notice. 5 billion years from now, the universe will be less than twice its current age, younger in cosmic terms than middle age. Stars in general will keep forming for a very long time. Not forever, but a long time. The era of star formation we currently live in is called the stelliferous era, the age of stars. It will last roughly 100 trillion years. That's 100 trillion years. Our current age of 13.8 billion sits somewhere near the beginning of that window. For the next 100 trillion years, stars will continue to ignite, burn, and die across the universe. New ones will form from clouds of gas and dust. The cycle will continue, but it will wind down. Over those trillions of years, galaxies will exhaust their supply of star-forming gas. Stellar nurseries will go quiet. The rate of new star formation will slow, and then slow further, and eventually drop to almost nothing. The last stars to form will be dim red dwarfs, small, cool, extraordinarily long-lived. Some of them will burn for trillions of years on their own, but they will burn out too. When the last star dies, the stelliferous era ends. What comes next is the degenerate era. White dwarfs and neutron stars, the remnants of dead stars, will persist for inconceivable lengths of time. White dwarfs cool slowly, radiating heat into space over quadrillions of years. Neutron stars are even more extreme. These objects will drift through a universe that is growing darker and emptier, coasting through the void with nowhere to go. The universe will be cold, quiet, dark in a way that's hard to picture if you've only ever known a universe lit by stars. This era lasts for something in the range of 10 to the power of 40 years. That's a 1 followed by 40 zeros. There are no analogies good enough for that number. It simply exceeds what human intuition can do. And then comes the black hole era. Over those extraordinary timescales, even the remnants of stars will decay through a process called proton decay, if it exists. Matter itself becomes unstable. What's left are black holes. Supermassive black holes, the collapsed hearts of ancient galaxies, will persist long after everything else is gone. They will be the last complex objects in the universe. Everything else, every atom, every remnant star, every molecule will have dissolved. Just black holes drifting through an expanding darkness. But even black holes don't last forever. Stephen Hawking predicted that black holes slowly radiate energy through a quantum mechanical process now called Hawking radiation. It's unimaginably slow. A stellar mass black hole would take something like 10 to the power of 67 years to evaporate completely. A supermassive black hole, the kind that sits at the center of a large galaxy, could take 10 to the power of 100 years or more. Those numbers are essentially beyond language, but eventually even the last black hole radiates away its final particle of energy, a faint burst of radiation into an empty universe. And then there's the dark era. No stars, no planets, no black holes, no structure of any kind, just an expanding void of cold photons, neutrinos, and the faint trace of particles too diffuse to ever interact again. The universe reaches a state called heat death, maximum entropy, minimum usable energy. Nothing happens. Nothing can happen. The universe exists, technically, but it does nothing. It goes nowhere. It just expands, forever, in perfect dark silence. This is what's coming. Not in any time frame that should cause practical concern. The sun won't even become a red giant for 5 billion years. But it's real. It's what the physics tells us. Every star you can see in the night sky is burning through a finite supply of fuel. Every galaxy is living on borrowed time. The entire stelliferous era, 100 trillion years of stars and light, is a temporary phase in a universe that will exist for lengths of time so large they have no meaningful names. We are here during the brief window when there are stars, when there is light, when there are planets with liquid water and atmospheres and creatures capable of looking up and wondering about any of this. That window will close. The universe will continue without us, without stars, without light, for durations that make our entire cosmic era look like a camera flash. On those timescales, even the stars are temporary. 2 trillion galaxies, each one containing hundreds of billions of stars, and around many of those stars, planets. Possibly billions of planets in our galaxy alone sitting in the habitable zone where liquid water could exist. When you run those numbers, the conclusion seems almost forced. Life should be everywhere. Intelligent life should have emerged countless times across cosmic history, in countless star systems, long before our sun even formed. So where is everyone? That question was famously posed by physicist Enrico Fermi in 1950. He was having lunch with colleagues at Los Alamos when he asked in a fairly casual way something that has never been satisfactorily answered since. If the universe is this old and this vast, and the conditions for life appear this common, then intelligent civilization should have had billions of years to spread across the galaxy. We should be able to detect them. We should have heard something. We haven't. That contradiction, the enormous probability that life exists elsewhere against the complete absence of any evidence for it, is what we now call the Fermi Paradox. To understand why the silence is so strange, it helps to think through the Drake equation. In 1961, astronomer Frank Drake developed a framework for estimating how many communicating civilizations might exist in the Milky Way at any given time. The equation multiplies together a series of factors. How many stars form each year? How many have planets? How many of those planets can support life? How many actually develop life? How many develop intelligent life? How many of those civilizations develop technology capable of broadcasting signals into space? And how long do those civilizations survive? You plug in your estimates and out comes a number. The problem is that almost every variable is uncertain. Depending on how optimistic or pessimistic your assumptions are, the answer ranges from less than 1 to millions. But even conservative estimates suggest that given the age and scale of the galaxy, there should be something out there. And yet the universe is quiet. Even plugging in values that lean towards scarcity rather than abundance, the math still suggests we shouldn't be alone. The numbers simply don't work. A galaxy with 100 billion stars and over 10 billion years of history should, by any reasonable calculation, have produced detectable civilizations. The probability works against the silence in almost every direction. We've been listening. Since 1960, when Frank Drake himself pointed a radio telescope at a nearby star and listened for artificial signals, we've made increasingly sophisticated attempts to detect signs of extraterrestrial intelligence. The SETI program has scanned large portions of the sky across multiple frequencies for decades. In 1977, an astronomer named Jerry Eman picked up a strong narrowband signal that matched the expected profile of an alien transmission so closely that he circled it on his printout and wrote the word "wow" next to it. It was never detected again. No confirmed signal has ever been received. No laser pulses, no structured radio transmissions. No megastructures blocking starlight in ways that suggest engineering. Nothing. These searches have spanned more than 6 decades of dedicated effort by trained scientists using progressively more sensitive instruments. Yet despite this sustained commitment and remarkable technological advancement, the results remain unchanged. Silence. This is what scientists call the Great Silence. And it's genuinely hard to explain. One possibility is the rare Earth hypothesis. Maybe life isn't common at all. Maybe the conditions that allowed life to emerge on Earth were extraordinarily specific. The right kind of star, the right distance from that star, a large moon stabilizing our axial tilt, a Jupiter-sized planet deflecting incoming asteroids, a magnetic field protecting our atmosphere, plate tectonics cycling nutrients. Strip away any one of those factors and maybe life doesn't get started. On this view, Earth isn't typical. It's a cosmic accident so unlikely that it may have happened only once or only a handful of times in the observable universe. The more closely astronomers examine planetary systems around distant stars, the more they recognize how particular our own system appears. The precise orbital stability of Earth, the chemical composition of our atmosphere, the sheer improbability of our arrangement. These things may not be copyable elsewhere. Another possibility is that life arises relatively easily, but intelligent life is the real bottleneck. Simple microbial life may be scattered across the galaxy, but the jump from single-celled organisms to complex tool-using, signal-broadcasting intelligence could be so improbable that it happens almost never. Life spent roughly 3 billion years on Earth as simple microbes before anything more complex emerged. That's most of Earth's history. Maybe that transition is the hard part, and most life-bearing worlds never make it. The emergence of consciousness itself remains one of science's deepest mysteries. We still don't fully understand how awareness arises from matter or why it should arise at all. Then there's the possibility that civilizations do arise, but they destroy themselves before they can spread or broadcast for long. Nuclear war, runaway climate change, engineered pathogens, artificial intelligence that slips out of control. The window during which a civilization is both capable of broadcasting and still surviving might be extremely short on cosmic timescales. A civilization that lasts 1,000 years before destroying itself is essentially invisible in a galaxy that's billions of years old. We've had radio technology for barely over a century. If that's a typical window, the odds of two civilizations broadcasting at the same time in a galaxy this vast are not good. There's also the possibility that advanced civilizations simply don't broadcast. Maybe they go quiet on purpose, either because they've learned something about the dangers of announcing their presence, or because their communication technology has moved beyond the radio frequencies we're scanning. We've been using radio for about 120 years. We're already moving toward tighter, more directed communication. A civilization millions of years more advanced than us might communicate in ways we can't detect and wouldn't recognize. Some researchers suggest we haven't been looking long enough or well enough to conclude anything. The number of stars we've examined in serious detail represents a tiny fraction of the galaxy. We've surveyed a small pond and called the ocean empty. Our instruments have real limitations. Our search strategies carry assumptions that might be entirely wrong. On this view, the silence isn't evidence of absence. It's evidence of how little we've actually searched. There's also a more unsettling possibility. Maybe civilizations do reach a certain level of development, but something stops them from going further. Something that stops all of them. A barrier, a filter, something in the long journey from simple chemistry to galaxy-spanning civilization that almost nothing survives. Whether that filter is behind us, something we've already passed, or ahead of us, something we haven't encountered yet, changes the implications dramatically. If the filter lies in our past, we may be among the rarest civilizations in the galaxy. If it lies ahead, we may be approaching an invisible threshold that awaits all intelligent life. We'll come back to that. What makes the Fermi Paradox so difficult to dismiss is that it doesn't require many civilizations to solve it. If even one civilization in the history of the Milky Way had developed the capacity for interstellar travel, and started expanding, even slowly, at just a fraction of the speed of light, it could have colonized every star system in the galaxy within 100 million years. That sounds like a long time. Against a galaxy that's 10 billion years old, it's nothing. We should see evidence of that. We don't. The universe has been running for 13.8 billion years. 2 trillion galaxies, numbers so large they become meaningless. And in all of that time, across all of that space, we have not found a single unambiguous sign that anyone else is out there. No signals, no ruins, no engineering on a scale visible from a distance, just the hiss of cosmic background radiation and the cold light of stars doing what stars do. The silence is the most unsettling thing about the universe. There's a concept in astrobiology that, once you understand it, you can't quite shake. It's called the Great Filter. The idea was first laid out by economist Robin Hanson in 1998, and it starts from the same place the Fermi Paradox does. The universe is enormous. It's ancient. The conditions for life appear to exist in countless places, and yet we see no evidence of any other intelligent civilization anywhere. Something is stopping them. Something is filtering civilizations out before they become the kind of species that spreads across galaxies and leaves traces we could detect. The question, the genuinely disturbing question, is where that filter sits relative to us. Think about everything that had to happen for you to be here. The Earth formed in the right place around the right kind of star. Liquid water persisted on the surface for billions of years. Single-celled life emerged. Then, after more than 1 billion years, some of those cells developed a nucleus. Then multicellular life. Then complex animals. Then vertebrates. Then land animals. Then primates. Then a lineage of primates that developed language, tools, and eventually the ability to ask questions like this one. Each of the steps took enormous amounts of time. Some of them may have been extraordinarily unlikely. Maybe one of those steps was so improbable that it almost never happens anywhere in the universe. If that's true, then the filter is behind us. We already passed through it. Whatever unlikely leap produced us, maybe the origin of life itself, maybe the emergence of the eukaryotic cell, maybe something else entirely. We got lucky. Incredibly, almost impossibly lucky. And most other potential civilizations didn't make it through that same bottleneck. That's actually a somewhat comforting interpretation. It means the silence of the universe isn't a warning. It's just a consequence of how rare we are. But there's another possibility. What if none of those steps were the filter? What if life arising, even complex intelligent life, isn't actually that rare? What if the filter isn't behind us at all, but ahead? That's where this gets uncomfortable. If the filter is ahead of us, it means something awaits every civilization that reaches our level of development. Something that stops them before they can spread across the stars. And whatever that thing is, it hasn't spared anyone. Nuclear war, engineered pandemics, climate collapse, artificial intelligence. Some technology we haven't invented yet that every civilization eventually discovers and that invariably destroys them. We don't know what it is. We just know the pattern suggests it exists. Because if civilizations routinely survive to become interstellar, we'd see them. We don't. The concerning reality is that we ourselves now possess the capability to become one of these filtered-out civilizations. We've developed weapons that could end our technological civilization in hours. We're advancing biotechnology without fully understanding the implications. We're approaching the creation of artificial intelligences that may transcend our ability to control them. If the great filter lies ahead, these are precisely the kinds of developments that have eliminated countless others before us. Here's the thing about the great filter that makes it different from most scientific ideas. It's not just a theory about the past. It's potentially a prediction about our future. If the filter lies ahead, then right now, today, we are on a trajectory towards something that has already ended every other civilization like us. We just can't see it coming. Robin Hanson put it plainly. We should hope the universe is as dead and lifeless as it appears. We should hope that every probe we send, every telescope we point at Mars or Europa or Enceladus comes back empty. Because as long as we find nothing, there's still a reasonable chance that the filter is behind us and that we're the exception, the rare survivors of a bottleneck almost nothing else gets through. Which brings us to Mars. Mars is the obvious first place to look for life beyond Earth. It's close. It once had liquid water on its surface. It may still have liquid water underground. Scientists have been analyzing Martian rock and soil samples for decades. The Perseverance rover is actively searching for signs of ancient microbial life right now. Most people assume that finding life on Mars would be one of the greatest discoveries in human history. A moment of triumph. Proof that we're not alone, that life is a natural consequence of chemistry and time, that the universe is full of it. And it would be a discovery, an enormous one. But think about what it would actually mean. If we found life on Mars, even simple, microbial, ancient life, it would tell us something specific. It would tell us that life is not that hard to get started. That given liquid water and basic chemistry, life tends to emerge. That the early solar system, with Mars and Earth sharing similar conditions, produced life in at least two places independently. Which means life is probably common throughout the galaxy. Which means complex life is probably not the filter. Which means the filter is probably not in our past. And if it's not in our past, it's in our future. That's what makes the Mars discovery scenario so quietly terrifying. Every time a scientist says we're close to finding evidence of past life on Mars, every time the data looks promising, a small part of the implication goes unexamined. We celebrate the possibility of finding our cosmic neighbors without fully reckoning with what their existence would say about our own odds. The Drake equation gives us a framework for estimating how many civilizations might exist, but the Great Filter is different. It doesn't just ask how many civilizations there are. It asks why there aren't more. It asks what the ceiling is. And the answer, whatever it is, applies to us just as much as it does to any extinct civilization on any dead planet, orbiting any quiet star in any corner of the galaxy. We are not exempt. We have no reason to believe we're special in that way. We're smart enough to have built the tools to look for life out there. We just may not be wise enough yet to fully understand what finding it would mean for us down here. Finding life on Mars might be one of the worst things that could happen to us. The universe doesn't just dwarf us in size, it dwarfs us in violence too. And that's a fact most people never really sit with. When we talk about the scale of the observable universe, we tend to focus on distance and emptiness, the vast stretches of space between galaxies, the silence of the cosmos. But that silence is misleading. What's actually out there isn't peaceful. It's catastrophically, almost incomprehensibly violent. The universe is running processes right now that would end everything we've ever known, and it wouldn't even notice. Let's start with gamma-ray bursts. These are the most energetic explosions we've ever detected anywhere in the universe. A gamma-ray burst can release more energy in a few seconds than our sun will radiate across its entire 10 billion-year lifetime. Let that settle for a moment. In the time it takes to read a sentence, one of these events pumps out more energy than our star will produce across all of human history, all of Earth's history, and billions of years beyond that. We detect several of them every single day, scattered across the observable universe. There are two main types: long gamma-ray bursts, which last more than 2 seconds and are associated with the collapse of massive stars, and short gamma-ray bursts, which are produced when two neutron stars spiral into each other and merge. Both are extraordinary. Both are terrifying. The beam of energy released in a gamma-ray burst is so concentrated, so narrow, that if one were pointed directly at Earth from within a few thousand light years, it would strip away a significant portion of our ozone layer. The hemisphere facing the burst would receive a lethal dose of radiation almost instantly. The other side of Earth would fare better in the short term, but the atmospheric damage would take years to repair. Models suggest it could trigger a mass extinction event comparable to the ones that have already reshaped life on this planet multiple times. The nearest known candidate for a gamma-ray burst is a star system called WR104, roughly 8,000 light-years away. It contains a Wolf-Rayet star, one of the most massive and unstable types of star we know of, and it's in a configuration that could produce a gamma-ray burst when it dies. Astronomers aren't certain it's aimed at us, but we're not certain it isn't. Neutron star mergers deserve their own attention. When two neutron stars collide, the event produces gravitational waves powerful enough to ripple across the observable universe and distort space-time itself as they pass through it. We detected exactly this in 2017, an event called GW170817. The collision also produced a short gamma-ray burst and generated a kilonova, an explosion so bright it briefly outshone an entire galaxy. It created large quantities of gold, platinum, and other heavy elements in the process. Most of the gold on Earth was forged in collisions like that one, scattered across the galaxy and eventually incorporated into the cloud that formed our solar system. The jewelry you own exists because neutron stars died violently billions of years ago. Supernovae are somewhat more familiar, but familiarity shouldn't dull the numbers. When a massive star exhausts its fuel and its core collapses, the resulting explosion can outshine its entire host galaxy for weeks. A galaxy containing hundreds of billions of stars, and a single dying one temporarily drowns all of them out. The shockwave expands outward at tens of thousands of kilometers per second. Elements heavier than iron are forged in the explosion and hurled into the surrounding space. A supernova within about 25 to 30 light-years of Earth would likely be lethal. Within the Milky Way, they happen roughly once or twice a century. Hypernovae go further. These are the deaths of the most extreme stars, events so energetic they blur the line between a supernova and a gamma-ray burst. Some of these objects are rotating so fast and are so massive that the entire core collapses directly into a black hole without a conventional supernova phase at all. The energy released in a hypernova can exceed a standard supernova by a factor of 100 or more. Then there are quasars. At the center of many galaxies, including our own, but in a dormant form, sits a supermassive black hole. When those black holes are actively feeding, pulling in enormous amounts of gas and dust, the surrounding accretion disk heats to extreme temperatures and releases energy on a scale that's almost impossible to frame in human terms. An active quasar can outshine its entire host galaxy by a factor of 100. One galaxy, hundreds of billions of stars, and a single feeding black hole at its center burns 100 times brighter than all of them combined. Some quasars are so luminous they were visible from billions of light-years away, even with the telescopes we had decades ago. We see them at the edges of the observable universe because they existed when the universe was young and dense, and black holes were consuming matter at extraordinary rates. Our own galactic center, Sagittarius A star, is quiet right now. It has a mass of about 4 million suns, but there's evidence it was far more active in the relatively recent past. A few million years ago, it likely produced a major outburst that blasted enormous structures called the Fermi bubbles out above and below the plane of the Milky Way. Those structures extend roughly 25,000 light-years in each direction. We're still seeing the aftermath. Here's the thing most people don't realize. None of this is unusual. None of this is rare by cosmic standards. Somewhere in the observable universe right now, stars are collapsing, neutron stars are merging, black holes are tearing apart entire solar systems, and gamma-ray bursts are sterilizing regions of space larger than anything we can meaningfully picture. This is the normal background state of the universe. We happen to live in a galaxy that is currently quiet. No nearby supernova candidates in the danger zone, no active quasar at our center, no detected gamma-ray burst aimed in our direction. We exist in a brief window of relative calm, and we don't know how long that window lasts. Nothing makes the scale of the universe feel more unstable than thinking about black holes. We've already talked about gamma-ray bursts and neutron star mergers. We've covered the kind of violence the universe routinely produces on scales that dwarf anything we can picture. But black holes are different. They're not just powerful. They're places where the rules we use to understand everything else simply stop working. The math breaks down, our physical intuitions break down, and the numbers, when you actually look at them, stop feeling like numbers at all. Let's start with the most basic kind. When a massive star, something at least 20 or 30 times the mass of our sun, reaches the end of its life, it collapses. The outer layers explode outward in a supernova. The core collapses inward with so much force that nothing can stop it. Electrons get crushed into protons, Protons get crushed into neutrons, and if there's enough mass, even that isn't enough resistance. The core keeps collapsing until it becomes a singularity, a point of essentially infinite density wrapped in an event horizon. That's a stellar black hole, the smallest kind, and they typically contain anywhere from a few to several tens of solar masses, compressed into a region smaller than a city. Think about what that means. The entire mass of our Sun, all 333,000 times the mass of Earth, compressed into a sphere about 3.7 miles across. That's the Schwarzschild radius for one solar mass. A black hole of 10 solar masses would have an event horizon roughly the size of a small town. You could drive around it in an hour, and yet it contains the mass of 10 suns. That comparison alone should feel wrong. It should feel like the kind of thing that can't be real. But it is. Now here's where scale really starts to collapse. Stellar black holes are the small ones. They're the ordinary, everyday, unremarkable version of this phenomenon. Because sitting at the center of the Milky Way, roughly 26,000 light-years from Earth, is something called Sagittarius, a star. It's a supermassive black hole, and it contains the mass of 4 million suns, 4 million solar masses, in a region that's estimated to be about 17 times the radius of the Sun. That's still small enough that it would fit inside the orbit of Mercury, but it has more mass than 4 million of our suns packed into that space. Sagittarius A star is technically quiet right now. It's not actively feeding in any dramatic way. For a supermassive black hole, it's relatively calm, and it's still one of the most extreme objects in the observable universe. Then there's M87. In 2019, the Event Horizon Telescope collaboration released the first actual image of a black hole's event horizon. It was a blurry orange ring against the darkness, and it made headlines everywhere. That black hole sits at the center of the galaxy Messier 87, about 53 million light-years from Earth. Its mass is 6.5 billion solar masses. Not millions, billions. Its event horizon is so large that our entire solar system, everything from the Sun out to the edge of the heliopause where Voyager 1 has barely crossed, would fit inside it with room to spare. The entire solar system, inside the event horizon. Gone. And M87's black hole isn't even the largest we've detected. There are black holes with masses exceeding 40 billion solar masses. Some estimates push certain quasar-driving black holes towards 66 billion. These are objects so massive that the concept of mass itself starts to feel inadequate as a description. So what actually happens at an event horizon? The event horizon isn't a surface you can touch. It's not a wall. It's a threshold, the point of no return, where the escape velocity required to leave equals the speed of light. Cross it, and you can't get out. Nothing can. Not light, not information, nothing. From the outside, we can't see past it. Anything that falls in disappears from our observable universe permanently. If you fell into a stellar black hole, the tidal forces, the difference in gravitational pull between your head and your feet, would stretch you into a thread of atoms before you even cross the horizon. Physicists actually call this spaghettification. It's a real term. A supermassive black hole is different. It's so large that the tidal forces at the event horizon are actually relatively gentle. You might cross the threshold without immediately realizing it. You'd be inside with no way out. And for a brief moment, everything might look almost normal. Almost. At the center of any black hole is the singularity. This is the point where general relativity, our best description of gravity and space-time, produces an answer of infinite density, infinite curvature. And in physics, when your best theory returns infinity as an answer, it means your theory has reached its limit. It means something is missing. We don't actually know what a singularity is because we don't have a theory of physics that works at those conditions. General relativity and quantum mechanics both apply in different regimes, and we haven't successfully unified them. The singularity is where that failure becomes unavoidable. And then there's the information paradox. Quantum mechanics says that information can't be destroyed. If you burn a book, in principle, the information about what was written could be recovered from the smoke and ash and heat. It's scrambled, but it's still there. But if you throw that book into a black hole, what happens to that information? Stephen Hawking showed in the 1970s that black holes slowly evaporate over enormous timescales through what's now called Hawking radiation. Eventually, the black hole is gone. But where did the information go? Did it come out in the radiation? Is it somehow preserved at the event horizon? Is it just gone, violating one of the most fundamental principles in physics? This is still an open question. Some of the best physicists alive are still working on it. We don't know the answer. A black hole manages to be simultaneously one of the simplest objects in the universe, described entirely by three properties: its mass, its spin, and its charge, and one of the most conceptually shattering. Something that contains 6.5 billion solar masses, but is bounded by an edge you could theoretically cross without feeling it. Something that breaks our best physical theories at its center while obeying them perfectly right up to that point. Something that can swallow entire star systems and grow larger and still be getting started. The stellar ones are city-sized, the supermassive ones are solar system-sized. And there are 2 trillion galaxies out there, most of them with one of these things at the center. At a certain point, the numbers stop being numbers and become something else entirely. To really understand the scale of the observable universe, it helps to go back to the beginning. Not to the first second, not even to the first millisecond. We need to go back further than that. To a moment so early in the history of the universe that the numbers involved stop looking like physics and start looking like a typo. About 13.8 billion years ago, everything that exists, every galaxy, every star, every black hole we've spent tonight trying to comprehend, was compressed into a region smaller than a single proton. Smaller than any particle you've ever heard of. The entire observable universe, all 93 billion light-years of it, packed into something you couldn't see with the most powerful microscope ever built. And then it expanded. What happened in the first fraction of a second after the Big Bang is called cosmic inflation, and the word inflation doesn't quite do it justice. In an interval so short that it makes a nanosecond look like a geological era. We're talking somewhere around 10 to the negative 36 seconds. The universe expanded by a factor of at least 10 to the 26. That's a number with 26 zeros behind it. The universe went from smaller than an atom to roughly the size of a grapefruit. In a moment that has no meaningful comparison in human experience. Here's what makes that so strange. Nothing in the universe today moves anything like that fast. The speed of light, which already seems impossibly quick, wasn't violated. Space itself expanded. The contents of the universe weren't flying outward through existing space. The space between them was simply growing. That distinction matters because it's the same process still happening today, just at a far more gradual pace. After that initial burst of inflation, the expansion continued. The universe cooled. Matter and energy began to organize. Within the first few minutes, the basic atomic nuclei formed: hydrogen, helium, tiny traces of lithium. For the next 380,000 years, the universe was so hot and dense that light couldn't travel through it. It was opaque, like the inside of a star. Then, as things cooled further, electrons combined with nuclei to form neutral atoms, and for the first time, light was free to move. That light is still traveling today. We detect it as the cosmic microwave background radiation, a faint glow in every direction, a snapshot of the universe as it looked nearly 13.8 billion years ago. But here's the part that connects directly to everything we've been talking about tonight. The large-scale structure of the observable universe, the filaments, the voids, the galaxy clusters, the cosmic web, didn't form randomly. It traces back directly to quantum fluctuations during those first instants of inflation. In the earliest moments, the universe was not perfectly uniform. There were tiny variations in density, fluctuations at the quantum scale, smaller than any particle. As inflation expanded the universe by that extraordinary factor, it also stretched those fluctuations. It took something microscopic and printed it across cosmic distances. Those slight overdense regions became the seeds of everything. Over hundreds of millions of years, gravity pulled matter toward those seeds. Gas collapsed, stars ignited, galaxies formed along the same patterns that were written into the universe in a fraction of the first second of its existence. Every galaxy cluster you've heard about tonight, the Virgo supercluster, Laniakea, the filaments connecting them across hundreds of millions of light years, all of it traces back to quantum noise from a moment that lasted less than a trillionth of a second. That's worth sitting with. The largest structures in the observable universe are the amplified echoes of the smallest possible fluctuations. Scale works in both directions. The incomprehensibly vast grew directly from the incomprehensibly small. Some physicists describe inflation as the universe's way of setting its own initial conditions, the uniformity we see when we look at the cosmic microwave background. The fact that the universe looks roughly the same temperature in every direction, even in regions that should never have been in contact with each other, is explained by inflation. Before the expansion, those regions were close enough to reach equilibrium. Then, inflation pulled them apart, far beyond each other's horizons. They look the same because they once were the same. What we don't fully understand is what drove inflation in the first place. The leading models involve something called the inflaton field, a theoretical energy field that existed in the very early universe and decayed as inflation ended, converting its energy into the particles and radiation that filled the universe afterward. But the inflaton hasn't been directly observed. It remains one of the biggest open questions in cosmology. We know inflation almost certainly happened. The evidence is extremely strong. We just don't know exactly what caused it or whether it ever truly stopped beyond our observable horizon. That last point carries some weight. Some models of inflation suggest that it's still happening in regions beyond our cosmic horizon, that other bubbles of space expanded into stable universes, each potentially with different physical constants, different laws, different histories. That's speculative, but it follows from the same physics that explains what we can observe. The universe we see may be one of an unknowable number of regions that emerged from the same inflationary process. What we do know is this: the event horizon of a black hole, the spiral arms of the Milky Way, the voids between galaxy clusters that stretch for hundreds of millions of light years. None of it existed 13.8 billion years ago. All of it came from a single point, smaller than any scale we can directly measure, in a moment shorter than any duration we have words for. Everything you've heard tonight, the trillions of galaxies, the 93 billion light years, all of it grew from that single moment. So where does that leave us? We've spent this entire video building a picture of something so vast it resists comprehension. 2 trillion galaxies, hundreds of billions of stars per galaxy, a cosmic web stretching 93 billion light-years in every direction. And somewhere inside all of that, orbiting an ordinary star in the outer edge of one unremarkable spiral arm, sits a small rocky planet about 8,000 miles across. That's us. That's Earth. Carl Sagan understood this better than almost anyone. In 1990, NASA turned the Voyager 1 spacecraft around when it was roughly 3.7 billion miles from Earth and pointed its camera back at us. The resulting image showed Earth as a single pale pixel suspended in a ray of scattered sunlight. Sagan called it the pale blue dot. In his words, every human being who ever lived, every king and peasant, every act of courage and cruelty, every civilization that rose and collapsed, every inventor and explorer, all of it happened on that dot, that mote of dust suspended in a sunbeam. Nothing in the cosmos singles our location out as special. We're not at the center of the solar system. We're not at the center of the galaxy. We're not in a particularly notable galaxy cluster. By every measure of position, we are cosmically average. If the observable universe were a city, Earth wouldn't be downtown. It wouldn't even be in the suburbs. It would be a single grain of sand on a sidewalk somewhere in the outer neighborhoods, in a city that stretches further than you could ever walk. Here's the thing most people don't sit with long enough. That's not a poetic exaggeration. It's a literal description of our situation. Astronauts who've seen Earth from space describe something researchers now call the overview effect. It's not just awe at the view, it's a cognitive shift, a sudden, visceral understanding that the borders we draw on maps aren't real, that the atmosphere is a shockingly thin layer, that the planet looks fragile in a way that no photograph fully prepares you for. Edgar Mitchell, who walked on the moon during Apollo 14, described it as an instant global consciousness, the feeling that something needed to change in how we treat the place we came from. Because from out there, you understand what it actually is, a single, isolated world with no backup. But here's where it gets complicated. Insignificance in scale doesn't automatically mean insignificance in meaning. Those are two different things, and we sometimes collapse them together when we probably shouldn't. Think about what has actually happened on this pale blue dot. Somewhere on this average planet, orbiting this average star, in this average galaxy among 2 trillion, matter arranged itself into living things. Those living things, over billions of years, became complex enough to develop brains. Those brains became complex enough to develop language, mathematics, and science. And then those brains, your brain, looked up at the night sky and started asking questions. How far away are these lights? What are they made of? How old are they? How big is all of this? The universe has been running for 13.8 billion years. For nearly all of that time, as far as we know, nobody was asking. Stars formed and exploded and collapsed into black holes, and no mind anywhere registered it. Galaxies collided in events that released more energy than anything we can describe, and there was no one to witness it. The cosmos was doing all of this in complete silence, without an audience. And then, on one small world, it produced something that could watch. The odds of this happening seem vanishingly small. Intelligence is not inevitable. It's not written into the laws of physics. Every condition had to align precisely. The planet had to form at exactly the right distance from its star, with the right composition, at the right moment in galactic history. Too close to violent stellar neighbors and radiation would have sterilized any emerging biosphere. Too far and the world would be a lifeless, frozen cinder. The window of habitability turned out to be remarkably narrow. And then, on top of that narrow window, life itself had to develop complex enough to become conscious and wonder about the cosmos it inhabits. That's a strange fact to sit with. We are, in a very literal sense, the universe becoming aware of itself. The hydrogen that fused in the cores of ancient stars became the carbon in your body. The calcium in your bones was forged in a supernova explosion before our solar system existed. You are made of the same stuff as the cosmos, and somehow that stuff has arranged itself into something that can look back at where it came from and recognize it. That doesn't shrink the terror of the scale. It doesn't make the distances shorter or the darkness less vast. You can hold both things at once. The cosmos is not designed around us. It's not scaled to us. It doesn't care whether we survive or not. A gamma-ray burst could sterilize the surface of this planet, and the universe would continue without registering the loss. We're not protected. We're not central. We're not the point. And yet, we're the only thing, as far as we can determine after decades of searching, that has ever looked up and understood any of this. No signal has reached us from any other mind in any other place. The sky is silent, and in that silence, on this one world, we built telescopes and particle accelerators and space probes, and we pieced together a picture of something 93 billion light-years across that began in a moment smaller than a proton. That's not nothing. Whether it's enough to call meaningful, whether it compensates for the loneliness of the scale, is a question science can't answer for you. Some people look at these numbers and feel liberated. If nothing is cosmically important, then the pressure lifts. Others look at exactly the same numbers and feel a weight that doesn't go away. Both reactions are honest. What we can say is this: the observable universe is unimaginably large, unimaginably violent, and almost entirely empty. It has been running for 13.8 billion years and will continue for trillions more. The window in which creatures like us exist is almost too narrow to measure against those timescales. But the window is open right now. We are, as far as we can tell, the only part of the universe that knows the universe exists, and that is either the most meaningful thing imaginable or the loneliest. There's one more layer to this that's worth sitting with. We've spent tonight talking about scale, distances, time scales, numbers so large they stop functioning as numbers. But there's something underneath all of that which is stranger than any of the figures we've thrown at you. The observable universe isn't just a description of how far space extends. It's a description of the limits of what we can ever know. And those two things are not the same. Here's what that means in practical terms. The cosmic horizon isn't a wall. There's no physical barrier sitting at the edge of the observable universe. No membrane you'd pass through. It's simply the distance beyond which light hasn't had time to reach us since the Big Bang. The universe is 13.8 billion years old, and light from anything farther than roughly 46 billion light years away hasn't arrived yet. So we can't see it. Not because it isn't there, because the information about it hasn't reached us, and in many cases, it never will. That distinction matters enormously. What lies beyond the cosmic horizon is almost certainly real. It exists. It has structure. Galaxies, stars, possibly planets, possibly life. We have no reason to think the universe simply stops at the edge of what we can observe. Every model of cosmic inflation suggests the full universe extends far beyond our observable bubble, possibly by an almost incomprehensible factor. Some estimates put the full universe at a minimum of 250 times larger than the observable portion. Others suggest it could be thousands of times larger. Some models allow for it to be effectively infinite. We don't know. And here's the unsettling part. We may never know. It's not a technology problem. It's not that we need a better telescope or faster computers. The information isn't coming. The photons from those regions will never reach Earth. We are permanently structurally cut off from that knowledge. The cosmic horizon is a hard limit on what the universe is willing to show us. Some physicists push this even further. If the universe is genuinely infinite, or even just vastly larger than our observable slice, then the physics in these distant regions might not look like ours. The constants we treat as universal, things like the speed of light, the strength of gravity, the charge of an electron, might vary across regions of space that are forever inaccessible to us. We call them constants because they're constant everywhere we've been able to measure. But we've measured an extraordinarily small piece of everything that exists. There's no guarantee that the rules we've mapped apply universally. We simply assume they do, because what else can we do? Some cosmologists argue that the question of what the full universe looks like isn't just unanswered, it may be unanswerable in principle, not temporarily unanswerable, waiting on better science. Permanently, philosophically unanswerable. The concept of the universe as a single knowable thing might not be a coherent concept. You can only describe what can, in principle, be measured. Everything beyond the horizon falls outside that category entirely. Whether it's meaningful to call it part of our universe at all is genuinely disputed. That's a strange kind of vertigo to sit with. Most of the time when we say we don't know something, we mean we haven't figured it out yet. This is different. This is a domain where knowing isn't available as an option, and it compounds. Because even within the observable universe, our knowledge has limits we tend to gloss over. We can map the cosmic microwave background, the oldest light in the universe, sitting at about 380,000 years after the Big Bang. Before that, the universe was opaque. Photons couldn't travel freely. What happened before that point, the first instance of inflation, the conditions at the singularity, we reconstruct from theory, not from observation. Our direct view of the universe doesn't extend all the way back to the beginning. There's a wall there too. So we have a horizon in space and a horizon in time. Two fundamental limits on what observation can tell us. Everything we think we know about the universe is built from a thin slice of information bounded on every side by what we simply cannot reach. What's remarkable is that we've figured out as much as we have. Working inside those constraints with light as our only real messenger, humans have mapped the cosmic web, traced the large-scale structure of 2 trillion galaxies, measured the age of the universe to better than 1% accuracy, and reconstructed the conditions of the first fraction of a second after the Big Bang. That's an extraordinary achievement given how little we're actually allowed to see. But it means the map will always have an edge, and beyond that edge is not empty space. It's not nothing. It's an unknown that has no path to becoming known. The universe may be doing extraordinary things in those regions. It may contain structures we have no framework to even imagine. We will never find out. There's a specific kind of humility that comes from realizing you can't even estimate how much you're missing. We know the observable universe spans 93 billion light years. We know it's almost certainly a small fraction of the whole, but we can't say how small. A tenth? A billionth? A number so small it has no name? All of those are consistent with what we can observe. The full universe has not handed us enough information to answer that question, and it's not going to. The edge of the observable universe isn't the edge of what exists. It's the edge of what we're allowed to know. Tonight, we've tried to do something that's probably impossible. We've tried to hold the observable universe in our heads. Not just the numbers, but what the numbers actually mean. And by now, you probably have a sense of why that's so hard. Step outside tonight and look up. If you're somewhere dark enough, you can see a few thousand stars with the naked eye. That's it. A few thousand. Out of somewhere between 200 and 300 sextillion. What you're seeing isn't the universe. It's barely a whisper of it. Every single point of light up there is a sun, a real one. Many of them larger than ours, many of them older. Some of them are gone already, and the light you're seeing left them before humans existed. You're looking at the past. Every time you look at the sky, you're looking at history. And here's the thing most people don't sit with long enough. That sky humans have been staring at for 300,000 years, the same one that guided hunters and sailors and farmers, that inspired mythology and religion and science. That sky hasn't changed much, but our understanding of what's behind it has changed completely. The ancient Egyptians looked up at these same stars and thought they were lights in a dome. We look up now and know that behind each one of them is a system, possibly with planets, possibly with oceans, possibly with something we'd recognize or something we wouldn't. We still don't know. That's the part that's hard to sit with. The observable universe is 93 billion light-years across. It contains 2 trillion galaxies. Each of these galaxies contains hundreds of billions of stars. And all of that, every bit of it, is just the part we can see. The part bounded by our cosmic horizon. Beyond that edge, the universe continues. We don't know how far, we don't know what's there. The laws of physics may hold, they may not. We genuinely have no way to find out. We are here on a pale rock, orbiting an average star in the outer arm of a fairly ordinary galaxy, inside a local group that is itself a tiny corner of a supercluster that is itself an almost invisible filament in the cosmic web. Nothing about our location is special. Nothing about our size is significant. By every cosmic measure, we are negligible. And yet, we figured it out. Not completely, not even close. But we looked up, and we kept looking, and we built instruments, and we asked questions, and we pushed the boundary of what we could see further and further out. We measured the distance to the nearest star. We mapped the large-scale structure of the universe. We photographed a black hole 55 million light-years away. We did that. Something that emerged from the same physics as everything else somehow became curious about the physics itself. That's strange. It doesn't make us cosmically important, but it is strange. The scale of the observable universe is terrifying. That's the honest word for it. Not awe-inspiring in a comfortable way. Terrifying in a way that can make you feel small and brief and accidental. And those feelings are accurate. We are small and brief. Possibly accidental. But we're also the only things, as far as we know, that understand any of this. The universe doesn't know it's 93 billion light-years wide. We do. So go outside tonight. Find a dark spot if you can. Look up at those few thousand stars. Think about what's behind them. Think about the 2 trillion galaxies you can't see. Think about the edge of the observable universe, 46 billion light-years away in every direction, and what might lie beyond it. Let the scale land on you fully. Don't push it away. It should feel heavy. It should feel a little frightening. That's the right response. If tonight gave you something to think about, spend a moment supporting this video by liking it or subscribing. It means a lot, and it helps us keep making these. Good night, and may your aspirations stretch toward the cosmos.